Alright, I'm going to start. Nice cat, Emily. Alright, so we are the middle of page 239, at least in my version. Factors affecting bacterial growth. You should be able to figure out a couple of them. Any takers on this not so bright and beautiful morning? So what factors could affect bacterial growth?
Temperature, moisture, oxygen.
Yeah, absolutely. So temperature, moisture, can you put it a different way? So temperature and oxygen, absolutely. But it's not quite moisture.
Humidity.
No. Any ideas? So what things do you know that would make cells shrivel or burst?
Meiosis.
Not meiosis, you have the right ending.
Osmosis.
Osmosis. So it's kind of more salt concentration rather than moisture. Okay, so in terms of our factors, they essentially relate to how the bacterial enzymes are going to work. So things like temperature and pH will work for this. If you have too much or too little of any one of these factors, it's going to influence the growth of your bacteria. So things like temperature, the oxygen concentration can have a huge impact. pH, we've said. So external solute concentration is a posh way of saying either the cell is going to burst or the cell is going to shrivel. So what is the salt concentration or the concentration external to my little bacterial cell? What's that going to do to the cell? Is it going to make water rush in or rush out? And then the last one is pressure. Okay, so if you think that we have bacteria that live in the deep sea vents versus in the top of the Himalayas or in ice cores where pressure is different, then pressure will have an effect.
Miss, I can't see anything on the screen. I don't know if it's just me or...
Okay, because then thank you. Sorry. Thank you, Anna. Keep me on my toes. So then we have the idea of a limiting factor. So my chemists should have a better idea, but can we put it into a biology context? What do we think a limiting factor?
It slows down the reaction.
So in a biology speak, it's going to influence how good your bacteria are going to reproduce. So in chemistry it determines your product, but in biology it's going to limit growth if there is a limiting factor. So in terms of temperature, what do we think might be the optimum temperature for vast majority of bacteria?
40 degrees?
So for some of them, absolutely. So the ones in your washing powders nowadays have 40. Bacteria are kind of like plants, in that 20 to 30 is a good temperature. We know now that if we have too high temperatures, their enzyme will be denatured, but there are enzymes that will work at really, really high temperatures. And we also know that low temperature will just slow down their growth because the rate of reaction is going to be slower. Okay. So oxygen, we've already done aerobic and anaerobic, but now we're going to add to those. So obviously aerobic bacteria will require oxygen for their respiration.
Miss, can you go back to the last one for a minute, please? Thank you. Okay, thank you.
Okay, so we've done the aerobic and the anaerobic. So all you really need from this is the fact that they will require respiration. This is a big, huge bioreactor, and if it's an anaerobic process, then they will, if it's an aerobic process, they will bubble it into the bioreactor to make sure it's getting enough oxygen. So this is what you need. So similarly, if aerobic require oxygen, the anaerobic don't. And we have two versions of, or two words to describe what type of anaerobic bacteria they are. So we have a word facultative and we have a word obligate. So facultative anaerobe and an obligate anaerobe. So facultative anaerobes don't care whether oxygen is present, they're just going to get on with it. They don't need it, but they'll get on with it. So the E. coli that live in your intestines, they are facultative anaerobes. And I think I have to go over the page for the next one. So the obligate, if you're obliged to do something, you have to do it. So an obligate anaerobe can't have oxygen present. They have to have pure anaerobic conditions. So you don't really need the examples, I'm just giving them to you for a context. It's just our definitions. Okay, so we've already done pH when we did our enzymes. So obviously if it's unsuitable, the enzymes become denatured. The vast majority of bacteria will grow around pH 7, but we have some exceptions. There's different parts of our planet where it's either very acidic or very alkaline. This actually, the Helicobacter has a real relevance in Ireland. So Helicobacter presents as stomach ulcers, and the Irish population has a huge, loads of people have Helicobacter infections in them. It's very weird. So one of the places I worked with in kind of the group next door to me, they were working on ways in which to treat Helicobacter at pH 2 in your stomach. Okay, so then we go on to the external solute concentration. So we saw when we did bacteria, or when we did osmosis and food preservation, the idea that if we put...
Can you go back to the last one?
We good, Miles?
Yeah.
Okay, so we saw in food preservation that if you put bacteria into high salt or high sugar, they will lose water by osmosis. So that's one way it does it. Ooh. So the solute could be salt, it could be sugar. It's going to be anything that's dissolved in the water that's going to change the water concentration. Okay, so the last one I think on the list is pressure. Yeah, we're going to leave that out because it's not relevant. Pressure, we're going to say, so most bacteria will be killed by high pressure. Even their walls won't be high enough to tolerate it, but in the deep sea vents, obviously they can. And they will actually use those bacteria and their enzymes in genetic engineering for okay, are we okay to move? Yeah. Alrighty, so they can ask you to give examples of beneficial bacteria and harmful bacteria, and you can just pick 2 from the list. So if you can think of anything to do with usually food production, that's really, really helpful. We're going to talk about antibiotics next. We have this from when we did digestion, the fact that the bacteria in our colon produce B vitamins for us. We use genetically modified organisms to make insulin. And we have the bacteria in your carbon and your nitrogen cycle. For the harmful, it's usually anything that's going to make you sick in some way. So pathogenic bacteria in humans, in animals, in plants. They cause food spoilage, tooth decay. So sometimes these are the most common ones.
Do we just write 2 of these into
Yeah,
the box?
so you just pick 2 that are going to stay in your head.
Could you say rennet instead of lactobacillus or something?
Just bacteria used in the manufacture of cheese. This is just the food chemist in me with names. You don't need them. So rennet is a different thing. Lactobacillus, by eating the sugar, reduce the pH of milk, and that helps it to turn into cheese and yogurt. Whereas rennet is like the enzyme that it goes after bits of the protein, and that causes the protein to coagulate. So they do two different things. So Charlie, Julie, Rachel, I think I'm going off you. So if you look like you're done. Rachel, you okay? Alrighty, so folks, antibiotics. We've probably all taken a course of them at some point in our lives. What are they, or what do they do, or what do they not do? Any takers? So why do you usually have to take them? Oh, lads. The energy.
Bacterial infection.
So bacterial infection. What other infection would they give you antibiotics for? So definitely for bacteria. What one shouldn't they give it to you for?
Viral.
So they shouldn't give it to you for viral. So they'll work for bacteria and they'll work for fungi. So in terms of this as a definition, it is always, always, always poorly answered. So antibiotics are actually chemicals produced by bacteria and fungi. And these things will either stop other bacteria growing or they'll actually kill them. And the benefit for us is they don't harm our tissue. So this is nearly always poorly answered. So you can have, they actually make antibiotics originally from growing up certain types of bacteria, and they produce the chemical, and then they will use that chemical for bacterial infections.
Wasn't penicillin the first antibiotic?
Penicillin is the very first antibiotic. I used to work across the building. It was, what is the hospital? It is in Paddington. I just know Imperial is across the road. Imperial College is across the road from it. It's not coming to me now, but yeah. And essentially the story is he went away. He didn't close some of his petri dishes properly. He left a window open to the street, and when he came back, I'll show you what he saw on his plate in a second. So one of the things that's going to ping for homework, as I said, is this TED Talk video. She is a little bit dramatic in how she presents, so if you want to watch it on 1.5 speed, you can, but it's dead interesting. The fact that antibiotics were only properly commercially available since 1945, and they were life-changing, and if we get to 2045 with antibiotics still working, we will actually be in a really good place. It's kind of scary, but it's definitely worth viewing. So this is what Alexander Fleming would have seen. So the white here on his plate, this is the bacterial growth. So it's plated all over his plate, and these are obviously antibiotic discs now. But what the antibiotic discs do is they make what are called clear plaques. So the chemical that's being released from those discs, and these were released from the penicillin, is killing everything that's on the plate. So they will work for bacterial and fungal, they will not work for viral. And obviously that was the big issue with COVID at the beginning, because we can't treat viral just by taking an antibiotic. So in the US, the vast majority of antibiotic production is actually used in keeping animals healthy till they can kill them. But also in the US, doctors, GPs produce or prescribe antibiotics for everything, and they're not going to work. And this is one of the issues then that we have with bacterial resistance. Okay, so they'll work for bacterial and fungi and they won't. And this is just, it was Sir Alexander Fleming, and now we genetically engineer them. And the reason we genetically engineer them is because of antibiotic resistance. Okay, I don't know why that's gone that way. All right, so in terms of our resistance, again, we talked about this the last day. If the plasmid gets a mutation, the bacteria can develop antibiotic resistance. They won't be killed and they will just continue to reproduce. So I think our table for that diagram is on page 236. So I think there's a reference and the reference is wrong. So it goes back to, it's on page 236 for me. So in society now we have a tendency to overuse antibiotics. So this is showing you healthy bacteria, antibiotic resistant, still has its cell wall, life is happy. Whereas here, it's now, cell wall has been broken down, it's leaked everything out, it is now dead. So this last bit is just an FYI. So now we have huge issues with bacterial strains that are now resistant to antibiotics, specifically in a hospital context. There are loads, like can be called multi-resistant Staphylococcus aureus. There is like methicillin resistant Staphylococcus aureus, but all there is now that we actually have resistant strains that are present. So we've already done this little diagram showing us how the resistance comes about. So all you need is one bacteria and your antibiotic doesn't work anymore. This will pay for me now. I will put this on because I won't play through this and I can't find it quickly. I'll put this as a link onto your homework to show you what this is a big ginormous agar plate. And they have different antibiotic in different places, and they cover this side of it, or they put a little bit of bacteria in there and they allow them to grow, and the bacteria are going to grow this way, and it kind of gives you a timeline at how quickly resistance happens and the fact that you only need one. So I'll put that link for you to watch it. This is the lady for the TED Talk and you can have a listen to her. Just so the last bit of this is in terms of the overuse. This is the big problem. So if you take antibiotics and you don't need them, then you give the bacteria a chance to become resistant. And if you get a course from your GP and you don't finish it, that is an issue. So you should always finish your course. Primarily because if you leave one bacteria there and it grows and it now becomes resistant, you have to get another prescription to clear it. So every time you have to be prescribed something, that increases the chance of antibiotic resistance. And that is not a good thing. There are supposedly 2 infections in the world. One I think originated in India, which is in one particular gentleman, and only 2 antibiotics will cure it. And so once those 2 don't work anymore, then that's something that's going to kill you. And there's actually 1 infection in the world that only currently 1 bacteria will kill it. So if you get your prescription, you need to complete your course, even if you feel better. So this can be a question that they ask: explain how antibacterial resistance occurs and explain how the influence of overuse of antibiotics can lead to resistance. And please make sure that you understand your definition and that you are using the definition correctly. So antibiotics are chemicals produced by some microorganisms to stop or kill other microorganisms without harming human tissue.